Well, thank you, Simon, for the introduction. My name is Ruiz. So I'm a GD in machine learning, well developer in the category of the machine learning, and also currently work for Texas A&M University as a research scientist. And today I will be sharing some of my experience working with Gemini for a while, specifically gonna focus into the multimodality features, where this model is able to understand text, videos, images, audio, and extract information from that. And the idea today is provide uh, this kind of models, how this model actually works under the hood, but also to provide some samples code that gonna give you some example of how you can get in start with these APIs. So if you are willing to contact me or reach out after the talk, just please do. So here is the QR code to my website. You can find information about my LinkedIn profile, some of the publication that I have on my background. So I will be happy to discuss with you further any kind of topic that we discussed today. But also, if you guys have any questions, I'm gonna be happy to work on. So today's agenda is I'm gonna focus further and try to explain some of the concept behind of what we call today generative AI, and we're gonna see also how we have shift from traditional machine learning models when we used to talk about like feature engineering, and how today we rely on more sophisticated deep learning architecture like transformers, and how this actually kind of opened the door to this new generation of deep learning architectures such as GPT-4 and Gemini. Uh, Also, I'm gonna talk about like what actually multimodal means in the specifically in the context of deep learning. And also, I just gonna start talking about further, uh, uh, specifically about Gemini and the Google Generative AI Foundation models. And then I'm gonna provide some practical examples and some code that you guys can use to have a better idea how you can put in practice these concepts. So if you are just here for the code and you just are excited about start playing around with these examples, so please scan this QR code and you're gonna have access to the uh, Colab notebook that I will be going through today to show how you can get in start with the Gemini API and how you can start using these multimodality features. Okay, so let's start it. So it's gonna first introducing the concept of machine learning. Probably you guys are already familiar with this concept and have a better understanding about what machine learning actually is. But probably there are some people here that is the first time that heard about machine learning. So this is what I thought it could be nice to have a few slides introducing about the concept of machine learning and how this field has been evolved in the last few years. So I'm gonna provide two specific definitions, one from a general perspective, more like a high level, and another more like a more scientific, more focused, more specific. So when we talk about machine learning, in a general thought, we mean design and implement and train computational algorithms to learn patterns and identify patterns from our data. That data could be a structured and non-structured, meaning it could be images, but also we could have like the data organized in a specific format. And that patterns that those algorithms are able to learn, so they can be used to make inference and make prediction based on the generate data. Or they can also further generate data, sorry. But if you want to provide more like a specific definition of what actually machine learning does is it consists on fitting a mathematical or a statistical model to the distribution of the training data set that we're gonna provide with in order to learn. Learn is key here, and for a specific or a given task. And that task could be, for instance, predict or infer the value of a continuous or a discrete variable, or even just learning the data distribution parameters over the training observation. So I can use that knowledge to generate the data. So when I I want to emphasize here that the models are able to predict continuous or discrete variables because when we meet continuous, we are talking about regression problems. So we talk about discrete predictions, just like cat, dogs, or just what number. So we are talking most about classification problems. But at the end, so what actually machine learning means, like I have a data set, so I fit that data set in one algorithm. So the algorithm means this set of steps of this procedure to find the best parameters that fit to my data. And then that combination of the data, the algorithm, and the best parameters creates what we call the model. And we can use that model to do predictions in real life, in new data. And all of this happened iteratively through a process that is called training and evaluation. And so in the way where we actually spend times trying to find the best parameters for the algorithms to do the prediction and improve the performance of our machine learning model. So it's what we call hyperparameter optimization, the process of just trying to kind of go and explore what is the best set of parameters. And this is important to understand because this is the kind of part where we have different kind of algorithms and different approaches to find these best parameters. For instance, neuronal networks, which is pretty much the state of the art today of machine learning. They try to find these parameters through optimization process. However, there are other kind of machine learning that works different. But at the end, we just have an algorithm, and that algorithms try to find from different ways to find this kind of set of parameters that fit with my data, and I can have a model that perform well doing predictions in non-seen data. So it's really important to understand the difference between the machine learning algorithms and the model. Sometimes kind of we get confused about that. Again, so the machine learning algorithm is about the procedure to find the best parameters. When we talk about model, it's just the combination of the algorithm plus after the training process to find these best parameters. And the model can be trained for different tasks, and in different ways. So I can train a model, I can train a predictive model, a generative model, or a reinforcement learning model. This is generally the application of machine learning that we find there in the state of the art. So however, machine learning is expand to other domains where, like we can apply other kind of techniques to learn from data. But when we talk about predictive model, it's just I'm gonna train a model to do classification, regression of clustering on dimensional reduction. And the way that actually I train those models is depend on the kind of tasks that I want to solve. So I can just provide the model with samples, and the model gonna try to understand or extract pattern from those samples and um, use that information to learn and then do predictions. And in the way that this kind of model actually are trained is using the supervised learning approach. But if I want, for instance, just to train a model or kind of fit a model to identify some characteristics in the data or features that somehow can help me to identify patterns or give me an idea how I can actually route the observation of the data in my data set. So then I can actually train or fit my model in a supervised learning way. And this is generally used for problems like clustering or dimensionality reduction. So again, when we talk about predictive models, so generally we refer to try to infer the value of a variable. So if it is discrete, so we are talking about classification. If the variable is continuous, we are talking about regression. Now, recently, so we start like so this kind of hype of generative AI models start kind of uh, getting more kind of so people right now is more interested in this field and how I can use machine learning to generate new data. And at the end, what we actually do is that we train our models. So the model is able to learn the distribution parameters of my data, or the training data that I pass to the algorithm with. And then once the algorithm is able to learn those parameters, so I can do sampling. And this is not actually rocket science. This has been for a while. If you get back to your statistics courses before, but we used to do, if we know, like what we used to know based on those courses is that if we know the parameter of a distribution, so I can do random sampling from that distribution. And generative model is pretty much about that. If I can feed a model to learn through an optimization process the parameters of a given distribution, which could be the data set of images of cats and dogs. So then I can use that information, that knowledge to generate the data. And so generally we can find two different kind of models. So when we talk about unimodal model is this model receives instructions and generate content in the same modality. Modality means receive text and generate text. And this is generally what we do with large language models. But they can be trained further in multimodal data sets. And what's actually going to happen is the model going to be able to receive instructions in different modalities like video, text, or audio, and using different techniques of fine tuning or kind of taking advantage of the sophistication of multimodal architectures. So the model is going to be able to generate data in multi-modalities. And this is what we call multimodal large language models. And general reinforcement learning is based on pretty much an optimization. We don't really present the algorithm with data. What actually happens under the hood is that the model itself is going to generate the data into what we call the learning environment. And then to that process, I can teach an algorithm to predict an actions. And so this is what we call reinforcement learning from human feedbacks. And if you guys want to get more information about that, this has been well documented, especially because today reinforcement learning recently have been getting attention after these kind of models that have been developed on top of LLMs to improve the performance. For instance, reinforcement learning from human feedback, where in the way that actually you can tell to the model or provide feedback with about like this is not the prediction that I expected, is through reinforcement learning from human feedback, where the human intervention provide a reward to the model, so the model can be able to understand how it need to be adjusted in order to improve the predictions. So, but we can do again more than just predict the value of a single variable, which is what we call predictive analysis. So we can also train the model to learn the distribution of all my data. And so the model can generate new sample from that distribution. And this is what we call generative machine learning. So pretty much about distribution sampling. So then we're gonna find today that the most common models that the most common kind of approaches that we find are predictive modeling and generative modeling. So again, the predictive modeling, we provide the algorithm with data. The algorithm is gonna try to learn the relationship between the data and the labels that I am provide with the algorithms, and using different statistical and mathematical approaches, so we can train a model, and this model can be probabilistic or deterministic. Probabilistics mean that I don't expect the model to generate the same output every time. Deterministic is when like the model gonna generate the same output for the same input. And the y prime, which is the variable that I want to predict, this could be discrete or continuous, but it could be also a probability distribution. And based on what the model learned from the provided label and data pair, so the model attempts to predict the value of the output variable. So what about like generative AI model? Generative AI model is generally we provide the model with an structured content, which means pictures, images, text. So the model gonna internally learn. We're gonna try to estimate parameters of the underlying distribution of my training set. And using that information, if I can attempt to predict the probability distribution that define my data. So I'm gonna have a trained model that is gonna be probabilistics, and I can use that model to predict natural language images, audios, etc. That depend on the modality of the model. So after learning the statistical properties of the training data distributions, so the model generates a random sample from that distribution. However, like Y, which is the new image that I am generating or the new token that I am generating, is expected to have the same statistical properties and structure of the training set. So then data could be a structure or a structure. And a structure means data that is generated through a natural or unorganized means. For instance, images, video, audio, like we are using our phones every day collecting pictures and so on. We are just generating data in a natural way. But we can also have a structured data that is generated through an intentional effort to organize and format the data in a specific way. But we can also have data that can be synthetically or artificially generated. So I can train a model again in the distribution of training set to generate new samples. That new sample is what we call synthetic and artificial generated data. And what we are referring to here specifically is to that data that is not directly created or derived from real world observations. Instead, we are like using a computation algorithms to create that information. Some of the use case of this synthetic and artificially generated data could be in those cases when I need to have more data to train my models in order to improve the performance, or also the data could be sensitive, or it's not like really straightforward to collect the data. And also for testing and validation, like I can use data augmentation techniques to create a validation test. But it's important to know that generative AI or generating data is not only about using ChatGPT, Gemini, these kind of models to generate new data. Like this concept again has been for a while, so we can use different techniques to generate data. We can use simulation. This is very often used in science to create synthetic data. So generally what we have is a mathematical model or computational representation of a real world system or process. And we can use that to generate new data and improve our algorithms or try to kind of evaluate a specific phenomenon in different conditions. So here is some of the examples that we can find in the state of the art. We can also have techniques like a digital twin. When digital is pretty much a replica of physical system, but where we can actually provide feedback with through the input from the physical world. That means that we're gonna have a physical asset, a digital model, but also a data link. The data links allow then both the physical asset and digital model share information between, and that information can be used in the process to optimize the task that we are trying to automate. So, and I'm gonna go further on this because this is not kind of the main topic here, but this is another way to generate data. And we have been using for a while statistical random sampling in the statistics. When I try to infer the parameters of a distribution, and once I have those parameters, I can do just random sampling. This is very much this is what you do in data science, specifically in statistics, inference statistics, like when you try to infer the parameters of a known distribution, and then you can do random sampling. And there are different ways to do so. But I can just use data augmentation techniques. Data augmentation techniques is I need to generate new data, but like just based on the training sample that I have, I can apply different transformation to my training samples. For instance, computer vision is is commonly used data augmentation to kind of augment the data set. So, and in the way that we do so is just applying different transformation on the sample that I have in my training set to generate different variation of the pictures, and we get generating new data. But we have the generative AI models. In the generative AI models, we have different categories. What actually we do is we train a machine learning algorithm or a deep learning algorithm. And so we present the model and train the model on a data set of real examples. And again, the model gonna try to learn the underlying parameter of the distribution. And then we can use that in the second stage, which is generation, where we use the trained model to generate new synthetic data. This is one of the applications that we can find. And there are different approaches to generate new data. I just put some example here in the context of computer vision, but it has been extensively applied in other domains. For instance, here, so we can see that there are I just like sampling two different methods to do so. We have GANs on the left side, and we have diffusion models. Both are deep learning architectures. One focus on generate new data or generate new images in this case. So in the GANs, we have two neural networks, the generator and the discriminator, and the generator creates a fake data. Is generating new examples. And I have another neural network that is gonna act as a discriminator that try to distinguish if the example that has been created or generated by the generator is similar to those samples that the neural network knows about the training distribution. So then he just pretty much classified the data in like real or fake. And then through an adversarial training, the generator improves at producing realistic data, and the discriminator gets better to detecting fakes images. And all of this happens through an optimization problem. So at the end, I have a generator that is pretty good generating new images, and I have a discriminator that is very sensible to classify new samples. But we also have other kind of more advanced techniques that recently have been shown up into the literature, which is, for instance, diffusion models, where we pretty much train the model into different latent representations of my images on my training samples, which, for instance, I have a data set of cats, and I train diffusion models into a noisy representation in different latent space. Latent space means, as you can see, we have different noisy images here. So the model gonna, through providing that information and those samples to the model, the model gonna be trained to be able to denoise, to do the inverse process, which is denoise the images and generate, and that way, so they can actually, these models can actually generate new images based on those noisy representation or latent representation that we are providing to the algorithm. So the result, coherent images generate from noisy. But at the end, and here we're gonna start more going into the advanced topics of generative AI, specifically about the multimodal models. So at the end, machine learning models only understand vectors and numbers. So what that actually means? Well, before or during the training of the algorithm, the data, which could be, and again, on a structure, must be transformed. For instance, applying different feature engineering techniques, feature engineering techniques is a different kind of method that we employ to transform our data and convert our data into a numerical representation that the model actually understands. Or this, the data can be also in code. We can train a model that is able to pack or represent the data into a different, using a different kind of feature space, and this is what we call embedding. So But in summary, we need to transfer our data into a into a vectorial representation and then project that into what we call fixture or embedding space. So that numerical representation can be handcrafted using, again, fixture engineering, or can be also learned during training. So I can actually train again a model to do so, to create a low latent representation of my data. So if I have an image, for instance, I need to somehow transform that image, which is 2 dimensions, height and wide, or and the channels, 3 dimensions, sorry, and we need to transform that into a vector. So how I can actually do so? There are different techniques, you know. And is in the fixture embedded in space, sorry, where actually the magic happens and where those algorithms actually are applied. You know, especially because vectors can be mathematically operated and compared. So that means that I can uh, take that data that could be images of cats and dogs, but also can be information about students or whatever, and I can transform that data into vectors. When I have those vectors, so I can create a fixture space. Fixture space is where I can project that data, because you know once the image of a cat become a vector, so I can actually project that image of a cat into the fixture space, and I can actually compare that vector with images of dogs, for instance. And I can actually be able to identify relationship between them. For instance, if there is any kind of clustering patterns that I can use for train a classifier, where the classifier is going to be trying to find the decision boundary to identify that this new image of a cat is belong to the class 1, class 2, or class 3. And this is exactly what is behind of the multimodal models. You know, the multimodal model is consists of train a model. So that model generally have the different kind of encoder blocks. And those encoders are gonna try to find a joint space where I can project multimodal data into a joint and unified representation. What that actually means is like, if I have videos, text, images, so I'm gonna try to train a model to see if somehow this algorithms is able to learn or transform that information into an embedding representation, into a vector representation, um, that I can actually use to compare these different concepts that come in different multimodalities. And the reason why we call joint embedding space is because we are trying to compare videos with text, with images, and so on. So the tricky part here is how I can actually teach, or how can actually the algorithm is able to learn that joint representation. Because I can train an encoder that take an image of a cat, which is three dimension representation of that cat, to create a one dimension or any dimensions representation of that cat. Generally is a latent space. Latent space means I try to reduce the dimensionality of the input data, but I want that representation that is created by the model is still having uh, the kind of the information of the cat. And another cool thing about having that way to train a model to create a vector representation of my non-structured data, such as images of audios or text, and project that into what we call embedding space, is that because we are dealing with vectors, so I can actually add context. Add context means I can add information to those vectors that somehow can give me some insight or information regarding like that this video of a cat playing in the park is related somehow with this picture of an image of a cat. And this is some of the application of the joint or the multimodal retrieval systems or multimodal learning or transfer learning. So again, the mechanism is through the embeddings, train a model to try to find the vector representation that project my data into a joint space, or there are other more sophisticated techniques like alignment. So then at the end, we have the input data. We transfer that data into a numerical representation. We project that into the vector space. We apply different machine learning algorithms or techniques. So I can compare those vectors, find relationship between them and so on. And then through a hyperparameter optimization process, I can get the best models. And when I have the best model, I can use that to do predictions. So to make an example, imagine that I have been asked you to develop a mobile app to classify flavor of pictures. So I can try to go pretty quickly through this because I know that I short on time, but to explain how we have moved from manually try to extract those features to the be able to learn those features through training a model. So before deep learning, we used to use traditional machine learning models based on feature engineering. So that means that the traditional machine learning algorithms used to be or used to rely on what we call feature engineering skills, or in your feature engineering skills to transform your data into numbers of embeddings. So that means that if I wanted to train that classifier of pictures, so somehow I needed to implement something that allowed me to transform this picture into an structured data representation that I can pass to the algorithm. So here, for instance, we are using image processing. We just take the picture, we segment, after talk with the expert, the expert told me that using the petal length and the petal dimension and the sepal dimensions, so I can use those features to recognize and classify different kind of flowers. So then my task is how I can actually extract those features, Well, so I can just have some level of automation, like for instance, try to segment only those regions in the pictures using like image processing techniques. But at the end, I need to have this structured data representation that I can pass to a machine learning traditional algorithms to be trained to classify the different kind of. But the key here is that I need to manually handcraft the feature extraction of those. But then with deep learning show up, and which is based on neuronal networks. So they come with this new approach of trying to automate the feature extraction process. So the same algorithm, the same problem now, to continue with the same sample is we have the images, but I don't need to manually extract the features anymore because the deep learning architecture is going to have a set of specialized layers in the architecture that somehow they can actually learn features from the data, and this is doing by applying different transformations to the images, and that enables the model to identify patterns that at the end can be used for the other component into the deep learning architecture, which is the classifier that is going to use that information to predict the label of the. But as you see here is pretty much that incorporating these feature extraction layers. So the process of extracting those features become automated. However, at the end, what they actually just generate is just a vector representation of the features, and those features can be passed further to another algorithm to do the classification. But one of the problems that we have with this kind of architecture is that we used to have like a specialized layers and building blocks for different types, for natural language processing, translation, speech. So then in 2017, when Google published the paper Attention is All You Need, they come with this mechanism that as long as you can transfer your data that could be images, text, whatever, into a sequence, you can feed that into the same architecture. And this was like a milestone in the deep learning world because now instead to have this specialized ladder for the different domains, so we have a single architecture that can be used and applied to the different tasks. And this is how Transformer opened the door to this new generation of deep learning architectures. And in the way that this new revolutionary neural network architecture did so was incorporating the attention mechanisms where again, so if I can take my data set and somehow represent my data into a sequence, so then I can apply different attention mechanisms, and which are just components of the neural network that they're gonna try to identify or focus in the more important parts of that input sequence. And another kind of fancy features that transformers come with was, for instance, parallelization. Unlike sequential model like traditional natural language processing architecture like NNNs or recurrent neural networks, transformers enable parallel processing of the sequence of the input data specifically. Um, so this parallelism leads to faster training times and more efficient utilization of the computational resources. And also this represents that the model is could be it's gonna have more scalability because, and this is gonna open the door to have what we have, for instance, today with Gemini that have close to 2 million tokens that I can pass to the transformer architecture. So then, while this innovative deep learning architecture was initially proposed to address the limitation of traditional NLP architecture, once these architectures show up, people start looking how I can apply that, which come to solve an NLP problems into other domains like computer vision. So, and what they actually say is like, as long as you can tokenize your data, so anything that you can tokenize, you can fit into transformers, you can fit that into transformers. But tokenization is generally a concept that comes from natural language processing. Which means I have a sequence of words, and tokenize that sequence of words means like I assign to each word a specific ID or unique identifier. So I'm gonna have my vocabulary represented through a set of numbers. So how I can actually do the same thing using images or so on. Well, so we do so, but incorporating some kind of like a patching. That means that if I can take my picture that you can see in this animation, if I can take this picture and generate patches of those images, so I can fit that in, I can create just a sequence and I can pass that into a transformer block that can generate the output that I expected. So here you can see, for instance, how they are using what we call like a uh, mixture of experts architecture block, where as you can see, depending on the modality, the router gonna figure it out which expert could process that sequence, that input sequence, and this somehow improve the performance of the neural network. And this is some of the concept behind of Gemini multimodality. So then at the end, what we have is like we have videos, audios, text. So we apply different transformations to tokenize the data. And once we have the tokens or the sequence, so we can feed that into the transformer encoder, and the transformer encoder is gonna try to find a way to project that multimodal information into what we call multimodal projection head, and then so on is gonna pass to the other transformer blocks. So then how I can solve the same problem that I have been talking about from how you can use feature engineering to solve this image classification task. And also you can use deep learning to do the same thing. Well, you can do the same thing with transformer. So the only thing is you need to transform your pictures in a sequence of patches. So you compare your images into a sequence of patches, you pass that to the transformer model. The transformer model is gonna try to create an embedding representation. Well, that we know that this is a learned low latent representation that the model is able to um, um, figure it out during the training process. And then, so this is just pretty much the process. You have the training, the images, so you just create the patches, you pass that to the encoder. And so once you have the embeddings, it's just kind of the similar to the concept of having the fixtures vector. So that's mean that when you have the fixture vector that represent the images of the flowers, so I can pass that to a feed-forward neural network or even another algorithm to do the classification. The transformer in summary pushed forward in the field of large language model and generative AI models by addressing key limitations of traditional NLP architecture. And this opened the door to this state-of-the-art model like Gemini, GPT-4, DALL-E, Codex, and so on, because they are the backbone architecture for many of these models. So this is what we call modern deep learning. Modern deep learning is about teaching an algorithms to find low latency embeddings vectorial representation of my data that I can use to compare into what we call the embedding space with different modalities, and this is different ways to do so, you know. So in deep learning, so these convolutional layers that transform the images into a vectoral feature at the end, what they are doing is trying to learn an embedding representation of my pictures, but I can also use more sophisticated architectures. And when we talk about multimodal is I have the image input, I have the text input, I have the audio input, and so on. It doesn't matter the modality, as long as we can train a model, specifically an encoder, that can create an embedding representation of a vectorial representation of each modality. So we can actually, because once we convert or transform those modalities into vectors, so we can pass that to different transformer blocks and even combine them. So at the end, I'm gonna have this image input of a cat, but also I can provide context through passing text that can use to the model, can be used to the model to train to do something else, you know? So then at the end, generative AI is a type of artificial intelligence that can create new content. This is by trying to teach a model or try to learn a model, try try to train a model to learn the distribution of my training set. So when the model is able to converge and find and estimate those parameters, I can use that for do predictions. And the artificial generate data is expected to have the same statistical properties and structure as the sample that I provide the model with during training. And so we have multimodal models that, as I mentioned before, so it's just I put a picture, what I'm gonna get out is a picture. But if I have this, so what I get from the model is gonna be um, a text. But we also have multimodal models that receive instruction and generate content with different modalities. For instance, here I am passing a picture, but I can also pass text. So at the end, what that's gonna happen is these two modalities gonna pass into different transformer encoders. So those encoders gonna create an embedding representation of the different modalities, and in that what we call a joint embedding space, where we just pretty much have the different vectors that come from different multimodal representation can be compared and can be also combined and can be also added. So I can add information and context and enrich that numerical representation to be able to generate new data or just do predictions. So if you guys want to know more about, so I have this is a really good paper, a comprehensive survey of generative AI content. So they provide how these models have been evolved in the last few years. And today we generally find two different models, generative language model and generative image models. As the number indicates, one is focusing in generate text and the other is focusing in generate or interpret or create images. But internally, what actually happened or how this AI, this kind of generative AI models work is they use a technical concept that is called AI guide content generation, which involves utilizing advanced algorithms to generate data based on the human instructions. So this is why when you go to Gemini and you write down, can you please create a poem or create a picture or create whatever you want based on this description or based on this text, or can you please paraphrase? What you guys are doing there is just providing the algorithm with guidance. So that's mean that that input text is gonna be transformed into the embeddings, and this is what the model gonna be using internally as context to refine the generation process. So that means that this process is typically have three stages. One, extracting the intent information from the given instruction, which is your prompt. Then transfer that information into what we call context in form of embeddings, because when I have that input into embeddings, so I can operate those vectors and I can add that or I can add context. And that can be passed to the foundation models in what we call the enrichment phase into the transformer block, which is here. And then based on that information, the model can generate new content, you know? So it's a really excited concept when we see how this actually model, how those model actually works internally, you know? So be able to, the more exciting part for me about this, the generative AI is be able to provide the algorithm with context to affect and influence the process of generating new data. I think that this is the key part behind of this sophistication and this kind of deep learning architecture. This is a really exciting mad concept because at the end, what actually happened internally is just a bunch of different vector operations that can allow me to take those vectors and do some transformation on it and transform that into embedding. This is why it's so much important to spend time doing prompt engineering, because prompt engineering will guarantee that you are creating at the end, the model gonna be able to create an embedding representation that provides with context to the model to generate what you expect. Okay, so moving on, so it's almost done with the. So we have one type of this kind of architecture, the generative architecture in large language models or MLMS, multimodal language models. So very high level, what is a large language model? It's a type of generative AI architecture that usually means 1 billion or more parameters transformer-based model trained to predict the next tokens. And this is done by, so we generally think that the model is able to predict all the text at once, but actually what happened internally is that these models are called they are autoregressive models. So that means that they do kind of like a loop and they predict one token at the time, and the previous token is used or is being used by the model to predict the next token and so on. This is why they call autoregressive, you know, because they generate one token, get back and try to predict the other token based on the previous. But at low level, you know, like we like code, we are uh, just two files in this, the weights and the architecture, the model. So when I have the weights, so I can just use the model for inference, you know, because the weight is all of those parameters that the model learned by during the training. And this is what we really need to actually be able to make the model do inference. So in simple words, the LLM is a model that has been trained in a bunch of data and has been trained to learn the distribution of social data to be able to predict uh, the next token. And in the way that do so is by assigning the probability of to each of those tokens and then refine the generation process by taking that information as a context. Then it's just take a huge corpus of non-structured data, feed that into a neural network based on transformers, and that model is going to be trained to predict next token. The next token is predicted using different techniques. So we can see some here, you know, like we have radio strategy, multimodal sampling strategy. There is a bunch of different contests. There have been different ways to generate a new token, but at the end is that. So then what actually multimodality actually means? Well, the multimodal refers to the capability of deep learning models to process and integrate multiple types of data or input modalities simultaneously. That means it's like how I can actually make the model to be able to process, understand, but also do inference on text, images, audio, video simultaneously. So this is actually what is the technology behind of Gemini. Gemini is able to receive text, audio, images, even videos. And this can be passed to the Gemini architecture, and internally this Gemini architecture have encoders to process the images and text and the different modalities to generate the output that we expect. So this is some of the application. Now, how language model become multimodal? Well, in multimodal transformer architectures, the primary goal is to establish a unified space. This is what we call joint embedding space, where my multimodal data representation, which is mean images, video, audio, can be effectively projected and compared. So as you can see here is different pictures, and because they are in the picture space, they can be compared. And as we expected, this picture of this raccoon is similar to this picture of this other raccoon, even if they have different pose. But we try to compare those points with another picture of another animal. So we expect to have a longest distance in the vector space. This process can be particularly challenging, especially dealing with different data types. It's not easy to find that unified representation. So a commonly used technique to address this challenge is the way that generally these algorithms, especially the encoders that generate the embeddings for the different multimodalities are trained, is using techniques like contrastive learning. This approach involves presenting the encoder with the positive pairs and negative pairs of the different samples. And what actually the encoder gonna try to do is minimize the distance between the representation that are similar and maximize the distance between representation between the different images. This is what we call multiple optimization tasks. What I mean is like I am not only training the model to minimize the loss of my neural network to do the inference. Instead, I have two different optimization tasks. One is minimize the distance between images, video files, audio, or modality that are similar to each other. But I am trying to do another optimization, which is maximize the distance between this picture of a cat and this picture of a dog, because they are different topics, different contexts. That means that I expect they are to be different numerical representation. You guys want to further learn more about all of these concepts? I highly recommend read further about these topics. Just show up there, because this is a really nice topic, but it's so much stuff to show up. So then let's talk about Google Generative AI models. So well, before I would like to show. Well, if you go to the website of Google, you're gonna find that it's not only Gemini, or you go to this website AI Google Discover or models. You're gonna see that we have Gemini in different sizes, different versions, but also we have Palm 2. We have Imagen, which is a diffusion-based neural network architecture based on that is able to generate images. We had Code, which is the transformer architecture to generate code. We had Chirp for audio processing and audio modalities, video. There are a bunch of different really nice articles when they explain further, and they go into the detail of all of these kind of really nice architecture. It's not only Gemini, which is what we just generally heard in some of the talks. So the reason why I think that Google, even though there is a lot of improvement to do in terms of the implementation that they did of LLMs with Gemini, in comparison with other kind of competitors, the reason why I feel Google is in the top of the list, on the top of AI, is because they are the people behind, they are the team behind of transformer architecture. They really understand how actually transformer works, how they implement it. And even though they actually open source because they publish the paper about it, attention is all you need. that fact that they come with this architecture, they somehow push them to having the top of be able in the future. And I know that we're gonna see a lot of stuff going on soon, and getting this new groundbreaking deep learning architecture. And this helps have seen some of the evolution of the different models that Google has been released from 2015 to 2024, where we are today with Gemini. Uh, Really cool stuff about AlphaFold, to predict the structure of non-proteins. So much stuff going on, and sometimes we generally just focusing on, oh, ChatGPT is in the hype, like it's really good generating, but so it's really worth it to go back and see also not only focusing in LLMs, but see all of these new sophistication we have some of generative AI architecture like AlphaFold, for instance, which Google, I know that this um, is work really hard on this science-oriented kind of deep transformer architectures. So then Gemini is the most capable and general model has ever built, and it's the result of a large language collaborative effort between Google and Google DeepMind and Google Research. And well, as you probably have heard in this series of talks about Gemini a lot, so the only kind of thing that I told myself to show up here was just mention that the Gemini use internally something that is called mixture of expert architecture to do the implementation. I have some, if you really want to go further, in general, to provide an intuition, the mixture of expert consists of multiple experts. Each of them are the different neural networks, generally based on transformers, and each of them are trained to process or to do different things. And generally, this could be based on the modality or based on the knowledge capabilities or so on. And we also have a neural network, what we call the gating network, that decides which expert to the input numerical or embedded representation going to be sent to. And then based on that is what actually Gemini can generate the output. I don't really going to expand further on that, but if you want to know more about this architecture, Hugging Face wrote like a really good review about mixture of express plane. And also, if you want to know more about Gemini low level, so I highly recommend this um, like Jeff Dean is the chief scientist of Google DeepMind and Google Research, where he just dropped up here some of the papers behind of the implementation of Gemini, including, like how they use a mixture of EPSER architecture to build Gemini on to try to kind of come with an optimal optimization for sparse models, which is sparse model are those, it's kind of like optimization for training multimodal and transformer-based deep learning architecture. And he dropped a bunch of different really cool stuff there. And they actually mentioned that they are working really hard to see if they can go up to, I think that 10 millions of tokens. But let's see. I think that right now we are just close to 2 millions, but I think that we are in a good path to get there. So human icon in different sizes. You probably guys already know that. You can access to all of these really fancy models through the Vertex AI garden. So you can go there and you can, in a few clicks, be able to implement and create an endpoint with this model. So you can actually use that from the, in your applications. We also have open model. Open model doesn't necessarily means that we have access to the code, but we have access to the weights, so we can actually fine tune them, and they are open. So, but if you want to, if you want to kind of go further into fine tuning, I think that the way to do so is just try to go for an open model rather than that like a, like Gemini provide different ways to fine tune Gemini with through an API. But if you want to really understand how these models can be fine tuned, just go for an open model and do like a um, hands-on example. Here is a notebook that I create for well it's not a notebook that I create. It's a notebook that I found that where they do fine tuning for PolyGemma, which is one of the new generation of Gemma, which is one of the uh, uh, open models of Google, and they explain how you can fine tune to perform different tasks. So with that, so this is the only that I have to share to you guys all today. So this is the ecosystem today. If you are like more low code, you don't really want to get into the low level implementation of this model and play around with this model from a low level perspective. You can just code and use the cloud providers where they generally have these APIs to interact with models like GPT-4, Gemini. So, but if you want to kind of have a better understanding how this actually model works, I highly recommend, and it's really worth it to try and play around with the open model and open source implementation of LLMs. And if you feel like you want to try like going even more from scratch, so well, there are different frameworks that have been optimized, like PyTorch, TensorFlow, JAX, for training those models. Or and you can also access the you can also access to the models that have been trained in the Hugging Face, in the Hugging Face uh, um, app, you know. So this is all for me. So if I prepare a notebook, I don't think that I have time to go to the notebook, but in general, what I wanted to show in that notebook that I early shared is that how to play around with the Gemini API for multimodal. So I start here importing the dependency that we need, some util function that I implement, for instance, like authenticate with Google Cloud. As you know, if you're gonna use you probably already heard is if you want to use Gemini, um, uh, so if you want to use Gemini through Google Cloud, you need to create a project and then you're gonna be able to authenticate from the Google Colab and be able to access to that. But this is some util functions. They are all documented. And I explain here explaining how you can use the Gemini API to do send a text-only request, but you can also go how you can go further and do video and multimodal prompts, how you do also audio. So it's pretty straightforward how you create a chat here. And in the model capabilities, I explain here how you can apply, how you can use the image understanding capability of Gemini, for instance, to interpret this kind of diagrams. And for instance, here I am asking to create the SQL code to create this, and he's able to create a schema. And or I can tell, can you please create the HTML code from this website mockup? So as you can see, the model does a really good job to creating the HTML. And also to do downstream stacks, what we call, where like I can use Gemini to do, for instance, image classification. So I can say, please do your best to classify and label the provide images and generate the response in JSON format. And I can pass a set of images and the model gonna be able to predict the label. The same way it can do object detection. I have this picture and I ask to detect the objects. And previously I defined to the best to identify the bounding boxes. And as you can see, the model is able to identify the label and the bounding boxes for the different objects. Can do video understanding. Everything is documented in the notebook, so it's not really need like a further explanation or going into the detail of the code because the code is so well documented. So please go ahead. And finally, I really wanted to invite you guys to contribute with this open source project that is called um, Gemini Playground. Gemini Playground is a high-level API. It's a high-level API to play around with Gemini, but some of the key things that these add on top is, for instance, you can do, let me show pretty quickly here. You can do something like repo, git repo from URL, and internally what Gemini Playground does is that this repo is kind of like a multimodal part. That means that it's able to extract the multimodal part from that repository, and it can pass that into the model, and the model gonna be able to for instance, create a README file from that code, or you can talk with your code, you can talk with your videos. And also we provide this UI, like I imagine that I have a section here, my data, so I can upload my data here, and I can say, for instance, can you describe the following image? And I can just see all my files here. This could be audios, could be a code repository, could be and then I send that to the model. And this is gonna be the description. So I recently make a pull request, and so what we did is we also gonna provide, imagine that I have a set of files, PDF, GitHub repositories, audio files, and I want to combine all of them into a RAG system. So we provide 3 different implementation of RAG. So we provide agentic tool to use RAG, we provide agentic routing RAG, and we provide LOT RAG. So 3 words different, but they have different applications. As you can see here, you can combine also function callings, and so all of this is available. We are right now working on trying to merge that pull request, and this is gonna be free, and you guys can clone the repository and play around with the uh, Gemini playground. So please feel free to contribute, to work on it, and let us know your feedback. And also, if you want to have more examples about Gemini, so I had provided this GitHub repository Gemini workshop with a bunch of different examples about the Gemini API, multimodality, function calling. You can go there and check out this repository, and you're gonna find how you need to set up your environment to start working with Google Gemini, what is the code structure, explain which of those files does, and so on. So thank you so much for your time. I hope this talk was useful, and I am open for question if you guys have any. Can you guys hear me?
Yes, Henry, we can hear you.
Yes. I don't know. I don't know
We
if.
have few questions in the chat.
Okay.
So someone is asking what is the new LLM? And a few more questions. Oh, also some people are asking if we can have the link in the slides sent over and the link to the notebooks as well.
Yeah. The list of the notebooks. You guys can scan this QR code, and you're gonna find the
Mhm.
link there. And also for the notebook, I will be sharing the notebook and the slides in the this Gemini workshop repository. So any other question? Yeah, neutral foreign model deployment. Yeah, this is what we are today. Like this is what we call model deep learning. It's just about like representing multimodalities in the embedding space and how we can operate those vector representation to
Henry, we
train
have a
model.
question here. Sorry to interrupt.
Mhm.
So new transformer and modern deep learning, how it is different?
New transformer and model deep learning, how it is different. Okay, so when I call about model deep learning, it's just not like a specific context. It's trying
Mm-hmm.
to refer to the fact that today we have different ways using transformer architecture to not only use embeddings to kind of influence in the way how this model generate new data, but also how I can use joint space or like the joint embedding space to combine multimodality data. So in the traditional deep learning architectures, so we didn't have this kind of way to combine different multimodalities in the same architecture. Right now we have that. So this is what we call deep learning. But indeed, it's not actually, there is no any difference between model deep learning and transformers. Actually, they are like the transformer is what actually means now model deep learning, because this just opened the door to the new generation of deep learning architectures.
Noted.
Also, just quick reminder, if you want to speak to ask questions, feel free to unmute yourself, speak. I think right now is kind of an open discussion Q&A, so feel free to, if you want to speak to ask questions, feel free to unmute yourself, ask questions.
Hi, thank you so much. I missed the beginning of this training presentation, and can I access the recorded video somewhere?
Yes. So in the chat, I have attached the link to our YouTube channel. You can access the recorded sessions from there, not just this session, but like all our sessions are recorded and we upload it on our YouTube, so you can check it from there. I
Okay,
can reshare the link in the chat again.
Can you share the link again?
Yep, I'm doing that. So you go.
Yeah, someone is asking about like RAG in the chat. I saw someone is asking about how you can do RAG with multimodal data. Well, so there are different strategies, but the most simple one is like if you have a model that is able to understand different multimodalities, you can use that model to summarize that data. So that means that I can ask the model summarize this video, this audio file, and once I have those different multimodalities in the text space, so I can transfer that into embeddings and feed my vector store. So then I can actually use that as a context. Again, if you guys really wanted to go into the detail of implementation of RAG, what I said in the Gemini playground, so we do like a pull request here that is called feature RAG. And I did like a 3 different implementation of RAGs. So merge retriever, agentic routed retriever, and agentic tool use. And you can just go there and try to understand in low level how these implementations were done, and so in a high level way to show that is, so as you can see, I implement something that we call multimodal summarization retriever. And this multimodal summarization retriever, what it internally does is it have a function that summarizes the documents using a summarization loader. And once I have that, so I can actually just pass that to the vector database. But when I have those documents in the vector store, once RAG is just about, and before to actually send the query directly to the LLM, so I just first do a pass through to my vector store database to find which vectors have like similarities with that input, and then I can use that as a context to feed into the prompt, and then it can be used further to feed the LLM. But you can go there, so it's well documented too, and I have a function that is called create retrieval from multimodal data. And look at that, I am combining images, code, video, PDF into the same RAG system. Another question?
Hi, Henry.
Hi, how are you?
I'm good. Thank you for very informative session. So I'm new to AI part and I'm learning here. So actually, I'm building one application related to stock market chart pattern base. So for recognition of that patterns, like there will be multiple candlestick patterns. So where I can start, like if I have a classification kind of like different patterns data, so which tools I can use to train with those data, and then I will pass the real-time chart information to get that, like hey, this pattern is matching, this pattern is matching, kind of things I'm trying to build. So where I can start?
So what kind of data you are dealing with? Is it text or
Image-based, I am thinking to provide like suppose image-based data, and
Okay.
from there it will detect the pattern inside that and provide that update.
Okay, so like my advice here, and this is for everyone, is if you are just getting started in machine learning, it's really worth it before to actually jump to start using sophisticated methods. Play around with those foundation models that I previously discussed. Like sometimes for the application that you have, go to try to use a multimodal models could be overkilling. So you can just try to use traditional deep learning architectures, or traditional machine learning models. And if you don't get the result that you expected, so then you can get back and try a model that is more sophisticated. There is a really good paper. We actually think that I shared it here, where so it's provide. Well, I can share a letter, but if you could reach me out in LinkedIn, so I can give you some links that can help you to find
Okay.
what is the best model that can work in your case. But you need to first be clear about what is the goal. What is the kind of task that I'm trying to solve. Is a classification, is a regression. So what is the kind of input data that I expected, and based on that, you can define if I should go for a deep learning architecture or even just using traditional machine learning algorithms could be enough. So this is a really important, especially in these times where everyone is talking about generative AI. If you really want to become a data scientist, it's really, really worth it to spend time to understand the foundation algorithm, traditional machine learning algorithm, how they work, before to jump into what we have today that is very much transformer and so on. Take your time
Okay.
to explore these algorithms, but feel free to reach out to me and I will be happy to help you to figure it out which could work better in your scenario.
Yeah, sure. And one more thing, how much data required in order to work with classification prediction? Like
But
minimal information.
so if you are
Yeah.
using deep learning and you're gonna train the model from scratch, you're probably gonna have a few number of probably a lot of samples, thousand of entries. But generally, what you do in a lot of the cases is use something that is called transfer learning, which is use
Mm.
a model that has been trained in another data set, and you can further adjust that model to your specific task. And in those kind of scenarios, you're not really, are not really kind of like high intensity data. You don't really require so much data. However, is be aware that what this model are trying to do is learn the distribution of the data. So that means that this is really important to understand that is the pen of the data that you pass to the model that the model is gonna be able to convert and eventually find the best solution. So that means that as long as you can provide with more data, it's better for the model because it's gonna have more generalization and learning capabilities. Yeah. But this
Okay.
is really tough. Generally what people expect is you say 500 examples, 200 examples, but this is not like a trivial word. This depends of the distribution of the data, and in order to do like have a good performance, you need to um, add more data as long as you can. But you can use different data augmentation techniques if in your case you don't have so much data, you can apply different data augmentation techniques to have a better data set. And you're gonna start saying in the metrics and in the performance of your model how significant is to add more data and to the model. So another question.
Sorry. Can you repeat again?
Yeah, so you're gonna start saying as long as like when you start like adding more data, you're eventually gonna start saying that the performance of the model is gonna tend to start getting better and better and better. But
Okay.
if your data is scarce or you don't have so much data, so go and try different data augmentation techniques.
Okay.
Next,
Yeah.
we have Vanishta asking the question. She has raised her hand. Can you go ahead, Vanishta?
Yeah, thank you. Hi, everyone. So, hi, Henry. My
Hello.
question is with regards a follow-up question to the RAG piece. So I wanted to know, you said that we can take some data from, you were showing like the GitHub or maybe a database of a company or something like that, and then pass it to the LLM. My question is, will the LLM then be using this private data from the company? How can we avoid that, but still have a LLM be using like public domain data, but not really using the private data? I don't know how to explain that, not to, in order not to share the private data of a company outside. So
Yeah, this is a really, really interesting question. Thank you for the question. And the point here is that be aware that LLM application, it doesn't matter if it's a chat, if it's a function calling application, it's a rack application, whatever you mean. At the end, it's just everything about context. How you inject into the prompt information that the model can have access to generate a better response. That means that it's really tough to avoid that leaking of information, because if you at the end what you are using is uh, um, a commercial model. So that means that you don't have how to uh, kind of avoid that, because at the end what you are using when you are doing a rack system is just that I have a let me look very quickly here. Let me show you very quickly one example.
thank you.
So this okay, so at the end what I'm saying is so all the LLM application that again could be a chat application, could be a rack application, could be a function calling application, could be a multi-agent application, whatever. So you are bringing information from your organization, and you are injecting that as a context to the LLM, because the documents are transferred into embedding. Those embedding are in an embedding database. So eventually, when you do the query to the model, so the rack system gonna try to find the relevant documents to your input, and it's gonna use those documents as a context to generate the output. So that means that even if you can just use a model that summarize the information from your private data, so you're still having some liquid of information there. So saying that, if you really, really are concerned about privacy, my uh, my uh, my advice is just go for an open model. Try with other kind of you can use Llama, or you can use Gemma, or try to find one of those open models that you can actually deploy in an on-premise infrastructure. On-premise infrastructure means in your own hardware, in your own server, or in your organization, instead to go for even though they complain that they don't kind of make public your data, it's really tough to control that. So if your information is really sensible and you want to have completely control of that, my suggestion is go for an on-premise implementation using open models like what I mentioned before.
Okay, thank you.
That answered your question?
Yes.
Cool. Mhm.
I might ask a quick question. Hi, this is Saitam. Thank you for the nice presentation.
Mhm.
I wondered how the context, right, the instruction influence the output of the model. I mean, the model at the end, as you mentioned, it expects, right, the next token in the sequence. So how the instruction and the guided context affected that?
Okay, yeah, this is a really good question. So, in the way that actually happened is, let's see if I can explain that. Here. Okay, so as I mentioned before, so the transformer architecture, so you have a bunch of different building blocks. When I mean building blocks is we have the multi-head or like attention layers, we have the normalization layer, we have a bunch of different layers from the input to the output, to generate the next token. So, but from a high level perspective, if we want to see transformer and trying to understand how the enrichment phase actually happened, is through here. We have the preparation phase, we have the enrichment block, the enrichment phase, and the prediction phase. In the preparation phase is you need to transform your input, which in this case is what you are mentioned, that you are trying to guide the generation process of the model through injecting tests or or trying to say, can you create a picture with this, and this, So you're gonna transform that input into an embedding representation. Because at the end, what's gonna happen in this enrichment phase is that embedding representation, which is, you can think about like a vector, is gonna be injected here, you see, as a context. And this could be mean just like a zoom between the try to add that vector and or you can combine two different prongs or but at the end, so what actually happened is here in the enrichment phase, so that text is gonna pass as a context to the model. So then the model, internally gonna just gonna treat that as a information that it can be used to generate or augment or enrich the output that it is planning to generate. And you can see here, for instance, this flower have a small round violet petals with a dark purple. So we are passing that. So then we are also passing the picture. And then, as you can see here, where the embeddings of the images and the text of the images are combined, you can think about like a plus operation or like a joint operation between these two embeddings. And this is what actually gonna affect, because this embedding is gonna be passed to the last section, which is to the last part of the neuronal network, with this prediction. And based on that information, he's gonna start to find which are the next token that has high probability to be related with that input that you are passed through. And this actually happened through a process that is called autoregression. Like autoregression models, and let's see if I can show like a picture. It's like this, you see? So you just predict one token at a time, but the previous token is used as a context to generate the next one. So recently, some researchers have been kind of discussing about this idea of the autoregressive model. Autoregressive model is not enough. So I think that this was so. But this is what we have in the state of the art today. So there are some limitations behind of this model that people is discussing in the state of the art, but Yeah, this is how actually that works. Like you generate one token at a time, and then the previous token is generated as a context and feed again into the transformer. So then at the end we have an output that is the concatenation of this is why we can do a streaming, because we are generating at one token at a time. We cannot do this kind of way to generate one token at a time. So we just need to wait for all the model generate the complete output. So this is why we have this option in the API that you can do streaming, because we can get access to the token that is coming and so on.
See,
I hope this respond your question. Yeah, but I can just provide different information, picture and so on, and all of that information gonna be combined into the embedding space. This is how we means add context, because add context is like enrich that vector representation to add colors or to add color or whatever, or.
thank you.
Yeah. Well,
However,
I don't think
in this picture,
Sorry.
right, it seems like there are two inputs to the model. But when we prompt the model, we give the instruction and the question all in one input, right?
mhm.
So how those get separated, like what you showed here in the picture?
In this case, you have only one unique representation,
Right,
and this is why when you don't provide, for instance, one picture or somewhere else that add context to the prompt, this is why always people is forcing you to do prompting engineering. Because sometimes you get short in trying to explain the model exactly what you mean if you don't be very specific in the prompt.
I see.
So
I
this is why people is saying, well, so these models are kind of ready, but you need to be kind of very dumb explaining what they actually want to generate for you. And this is why, because you are trying to explain to the model what do you want to do. So that's mean that as long as you add more context, which could be one picture, it could be another text, or it could be another video, so on. So that's mean that you are uh, adding more information or using RAG. This is why you use RAG, because you add more context, So you are providing more information to the model, so the model reduce the hallucination and try to get a better answer for you.
awesome.
When it's just the text, it's just the text. It's transformed to embeddings and passed directly to the transformer blocks and so on. But again, this is in those kind of scenarios when you don't have so much content, you need to be very precise with your front engineer skills.
Thank you.
No problem.
I think we are running out of time now. So if you have any other questions, you can reach out to Henry on LinkedIn and then he'll be happy to answer you all.
Thank you so much, everyone, and have a wonderful rest of weekend.
Thank you, Henry, for that insightful session on multimodality with Gemini. It was great to see you covering it in depth on its working and patiently answering it in detail to each of our questions. We can clearly see the depth of knowledge that you have. Thanks for sharing all your knowledge with us.
Thank you so
And I'm
much,
sure our,
everyone, for attending. Sorry.
yeah, and I'm sure that our folks will go back, dive deeper, and start building applications with Gemini now, and not just use it as an LLM to get their answers for the project.
Yeah,
Yeah.
this is what I expected.
Yeah.
Yeah.
Thank
See you
you.
guys.
So, yeah,
Mhm.
thank you, Henry. So, before we conclude, I have an exciting update for you all, guys. So, I know it's late already, but I want you guys to just stick for a few more minutes. Give me a second. Yeah. Okay. So, we are going to have a Gen AI challenge and it's going to start from 1st of July and will run for 14 days. So this is going to be a self-learning challenge where we'll provide you the guide, resources to learn, and everyday topics to cover. So by this, you'll be able to master the foundational concepts of GenAI starting from scratch, and you'll build the basics right. And you'll be able to cultivate a daily practice to enhance your skills continuously. This is because, see, what happens usually, most of us, if we are working or if we are in college, all our work, like time goes in our work and at the, or like in doing the assignments and, preparing for your tests. But we hardly get time to upskill ourselves on a regular basis. We'll think that we'll do it in the weekend, but then in the weekend, we will be like, we need a break. So you go out and the time just goes on. So just to break this barrier, we are having this challenge where you can indulge yourself and slowly start building consistency so that you can grow to a larger extent. And here in this challenge you'll also build small use cases with open source llms and many other frameworks like langchain. You'll use hugging face and all of that. And the best thing about this challenge is that you'll learn at your own pace, anytime, from anywhere. It's just that it's going to be for 14 days. We'll cover the foundations, and for each day we have a target, but you can do it like throughout your day, anytime when you are comfortable. So stay tuned for more details on how to join and excel in this enriching learning experience. So stay updated on LinkedIn, like do follow us, and also keep checking our website. We'll like float around the posters everywhere soon. So now to our fantastic audience, please hold on for a couple of more minutes. We have like a feedback form over here. So I would encourage you all to quickly scan this QR code and give your feedback to our Google team. So we basically want to understand your experience using Google AI technologies until now. And if you have any feedbacks, any suggestions or opinions, you can please feel free to put it over there. And if you have built any projects using Gemini, Vertex AI, or anything of that sort, you can fill in the details so that they can reach out to you and maybe feature your projects at their events. If you have filled the form, please drop a message saying done in the chat. That would be helpful for us. Oh, yeah. And remember, guys, don't forget to share your feedback on LinkedIn. Tag us for a chance to win a special award in our next session. So just put up whatever you learned. Tag Henry, tag us, and say what you like the most about this session and what is your next step. So anything of that sort. And I'm pausing for a couple of more minutes for you guys to scan this and fill the feedback form. Please do share the feedback, guys. It will be really helpful for us for improvising and delivering more impactful contents for you guys. Great. Thank you all for joining us today. Stay tuned for more exciting events